Hey robot makers, do you want to learn about the new Raspberry Pi AI camera, what it can do, how it works and how to use it? Then this is the show for you. So let's dive straight in. My name's Kevin, come with me as we build robots, bring them to life with code and have a whole load of fun along the way. Okay, let's get over to our keynote and make a start, shall we? Yes, this is all about the Raspberry Pi AI camera, which is a new product that came out, was it just last week? Didn't seem to be too long ago that was launched. So we're going to talk about what it is, some of the tech specs of this, what it can actually do, how machine learning works. We've covered this in a few shows before, but I thought I'd bring it all together in one kind of show, and then we'll do a bit of a demo and walk through one or two of the examples as well if we have time. Okay. So how does this thing work? So the new Raspberry Pi AI camera is a new camera module that has an AI accelerator built onto the camera module. And that means that instead of doing any of the AI acceleration either as a hat or on the CPU of the Raspberry Pi, it can actually do all that inference, as they call it, on the board itself, on the chip itself, on the camera module. So this is quite an innovation. They actually showed this at a hardware, was it Embedded Hardware World earlier this year, and then they didn't come out with the product for quite some time, but they've launched it last Monday. So there's the box, the AI camera module. I can see that it looks very similar to a regular Raspberry Pi camera module, but it has this intelligence built in. So it does the inference on the actual chip and then sends the video stream or the image stream with some metadata, essentially saying what it's detected in that image. And that means that it can actually run on lots of older boards as well. So it's the original Raspberry Pi that has the camera module, the camera connector on it. So it's a compact camera module from Raspberry Pi based on the Sony IMX500 intelligent vision sensor. It has a 12 megapixel CMOS image sensor on board and the inference acceleration for a variety of common neural networks models as well. We'll have a look at some of those in a minute. And this enables us to develop sophisticated vision-based AI applications without the need for a separate accelerator. So it's really exciting because we can use things like the Raspberry Pi Zero, for example, without having to have an accelerator on board. We can just do it with this camera module. And it works exactly the same. You just plug it into the same connector. Priced at around $70, so it'll be adjusted for your local currency there. So let's have a look at some of the features. So this has a 78-degree field of view with a manual mechanical adjustable focus. You get this little plastic wheel with it, which has some little connectors on there. You push it onto the lens and you sort of twist it round to manually focus it. That's just one of the downsides of this camera, actually, because you have to manually focus it. I thought we'd push past that now with the camera module 3. But that aside, it also has an RP2040 for neural network firmware management. So we'll look at the actual loading and unloading of firmware in a second when we do the demo. Works with all Raspberry Pi models using the Raspberry Pi camera cables, which is really cool. It means we can basically, if you have a Raspberry Pi, you can get this camera module and it will work, which is really neat. And it comes preloaded with the MobileNet SSD model. We'll have a look at what MobileNet SSD is in a couple of seconds as well. And it's fully integrated with LibCamera, Pi Camera 2, all the standard camera libraries that come with Raspberry Pi. It has 16 megs of onboard RAM for caching the AI models. So it gives you an indication of the kind of size of model that we can store in there. We can actually store multiple models and the cache will hold them and intelligently move them in and out. That's what the RP2040 can do for us. And it has a 12 megapixel Sony IMX500 intelligent vision sensor. That's that sort of blackish chip that's in the middle there. It's the same kind of dimensions, physical dimensions as the regular cameras. So the PCB board is the same with the hole spacing, but the actual depth of the camera is a bit taller because it has this extra stacked camera on it. It's got a couple of different sensor modes. You can do 4056 by 3040 at 10 frames per second, or you can do 2028 by 1520 at 30 frames per second. So it's kind of 4K or 2K, which is pretty neat that it can do those quite high speeds. So let's have a look at how this image processing works compared to the traditional ways of doing this. So on the traditional way, on the left there, we've got the camera module, has the sensor on it, just the camera CMOS sensor. We can capture some imagery. We then stream that over the camera, the CSI, this is the camera interface, and we then do some image processing. We do image signal processing on that. So the Raspberry Pi can do some image signal processing. It can, detect if there's a person in the image, that kind of thing, using typically OpenCV, CV Zone on Python, for example. Now you can optionally have the AI accelerator, which the Raspberry Pi launched earlier this year. So you can put on a Raspberry Pi hat that will then offload all that image processing, image signal processing to the hat, and it can do a lot of processes per second to detect objects, images, whatever the model is actually running there. So you can either do that with the accelerator hat, or you can just do it on the device itself. And really you need something like a Raspberry Pi 4 or 5, I would say, to do it without any kind of acceleration. Compare this to the IMX500 camera module, the new AI camera. So you can see that we've got the sensor, then we've got the image signal processor within the camera module itself, and there's this AI accelerator. It takes what they call tensor inputs. We'll have a look at what tensors are in a second, and then it can return both the image data as well as the output tensor, which is the positions of objects it's found in the image and where they are as well. So the architecture, this was a diagram that I've sort of scraped and improved a little bit from the Raspberry Pi website, as explaining how this kind of fits together from a hardware and software perspective. So at the very bottom there, we've got the hardware module itself. It's got this 128 megabit flash. That's more of like the speed, how quickly it can shift data around. We've got the Raspberry Pi RP2040 in the middle, and then we have the CSI2 receive, which is the camera connections. Then we've got the I2C bus and the camera bus, the CSI2, which is the new camera bus. They connect to the Raspberry Pi 2040 SPI driver in the Linux kernel. So that's when you update to the latest version of Raspberry Pi OS, it'll also do this kind of update for you as well. Then we've got the IMX500 sensor driver, and we've also got the CSI2 receive on the other side as well. And then this is where we have connections to the IMX500 hardware, so we can load that into the kernel space. And then we've got the lib camera, which is one of the Linux camera drivers that can work with a whole host of different camera modules. We've got the core code for that. We've then got the Raspberry Pi IPA IMX500 helper, as they call it. And then that can connect to things like the RPI apps, which is a bunch of applications where you can just grab a still or grab a video. You can do all that kind of stuff. And we've also got Pi Camera 2 as well, where we can run things in Python and get images and process them and so on. So that's kind of how it all fits together from a kind of architectural perspective as well. So some of the features, we'll have a continue looking at these. So it's ideal for performing visual data processing locally. So if you don't want to send up your AI to the cloud, for example, I've got one of these quite recently. This is a Watcher AI. So it's a little device. Looks very similar to that rabbit that came out a while ago. So you've got like the wheel on the side where you can press that and move around the screen. This does a lot of the processing on device and then can send the image data up to the cloud, for example. So if you need to do everything locally, you can do that using this IMX500 camera module. Okay. So the way that some of these models work, they can do classification, detection, segmentation, or a mixture of all three of these things. So segmentation, you'll typically see this on, say, like a Tesla car, self-driving car, where it can separate an object from its background. If you use like Zoom or Microsoft Teams, for example, that's segmentation, where it can actually punch out you from the background, and it can detect that you're moving around, that the background is still. So that kind of segmentation processing, that's really useful. Pixel by pixel gives you a nice sharp outline. Classification identifies what an image is. So is it a person? Is it a bottle? Is it a mobile phone? That kind of thing. And then detection tells you where in that image that classification occurred. So what's the X, Y, X, Y coordinates of that? What's the sort of bounding box of that? And they typically put a label on there as well, like house, tree, for example, in our on-screen thing there. So what about object detection then? So object detection is a branch of computer vision that deals with localization and identification of an object. So we use these a lot in the examples for the AI camera module. You'll see the person face detect and it'll say person, and it'll also give you some kind of percentage of how accurate it thinks it's guessed that. Object localization and identification are two different tasks that come together to achieve a single goal of object detection. Object localization deals with specifying the location of the object in the video or image, and object identification deals with assigning the object a specific label, class, or description. So we talk about tensors a lot in the code and in the example. So I wanted to just give you an easier visual way of understanding what a tensor is. So if a scalar is just like a number, a single number, a vector, if you think about a line with 2 points, that's a vector. It's got 2 points on there. A matrix is a whole host in 2 dimensions of values of scalars, and a tensor is kind of a matrix of matrices. So it has collections of, in our case, it'll be classifications and coordinates within the image. So that's just a way, when we think about what is a tensor, that's what it is. So I actually did a video, I'll put a link in the description, I'll put that in again. If you're trying to find that during the live stream, it's actually on the other stream that cancelled a couple of minutes ago. We actually built our own AI model on a live stream a couple of years ago using a Jetson Nano. So the way that we went about this, we created a label file. We created a bunch of rows in that label file for all the different things that we wanted to detect. I think it was different types of robot that I was wanting it to detect. We collect images of all those different objects. Typically you need about 100 each from different angles, different lighting conditions, near and far, so that it can really get an understanding of what that is. We then need to label each of those images that we've taken. We need to draw a rectangle around it and annotate that, this is a robot in this particular picture, and this is like a SMARS robot, for example. And we need to do that for each of the classes of objects that we want to detect. So another model I created a while ago in TwitcherPy was, I looked at what the top 20 birds were that you find in the UK gardens, and I found 100 pictures of each of those birds, drew the rectangle around them, and then run that through a model to create a bird detection one. One of the things I found in that particular exercise was that most pictures you find on the internet of birds are from the front. You don't see any from the back of the head, for example, because people don't tend to take pictures of backs of birds' heads. So yeah, you have to sort of fill in the gaps yourself there, or just have that where the AI can't detect that. So you then need to train the model. You need to retrain, for example, the MobileNet SSD. You can do that. You can take an existing one and retrain it on new data. And then we can convert it to this Opal Neural Network Exchange, or an ONNX model format as well. We then we have these classifications. This is like the folder structure that we need to do if we want to create our own model. So we do this imagelabel.py. If you Google that, you'll find the tools you need to create your own models. And we typically have 2 sets of data. We have like the training data, and then we have the test data. So the training data and the test data are not the same. If you try and test on your trained data, you'll always get 100% type results because it already seen those images, whereas you want to test it on things it's never seen before. So that's why I typically split them in half. So here's an example of the testing I did with the models I created. So I had an Auto DIY, I had a SMARS robot, a SMARS Mini, and a Quad SMARS, the sort of walking robot. So I created a label file that had those 4 different classifications. The model we'll be looking at shortly, the MobileNet SSD, that can detect over 1,000 different objects. You can have a look at those as well. And then we need to take lots and lots of pictures. So I found a tool online, which is one of these ImagePy. You can see that we draw a rectangle around the thing that we want to take. We then move the model slightly. We then take another picture. We have to then draw the rectangle around it, like so. That specifies what the label is. And it helps us kind of do that quickly because it can cache the last label you used. Then you can move it again, take another picture. So it takes quite a while to build up these models. So you can see there, that's what I had to do to get it to detect that. And then you can put it in combination with different ones, have bits slightly obscured. The more training that you do, the better that your object detection will be, the more different types of image that you can get there. So you can see that goes on for quite some time. So that video is available in the description. So the process flow for this then, so we load into the data model, we fit the training model with the training data set. We then test the model with the test data. We adjust the weights. This is what automatically happens. We don't do this ourselves. The model training does this. And then we train again until the results are acceptable. We'll get a result back telling us how accurately it's guessed things. And we get that to, maybe above 90%, and we're happy. So how does image processing work? So if we take a picture with our camera, that picture is really just a bunch of pixels, picture cells, and they're made up of red, green and blue values. Each one might be a value between 0 and 255, for example. What we want to do with a lot of machine learning is take away the colour, because that information actually doesn't help us. It's easier to process if there's less data. So we put the image as a grayscale, we can convert it to a value between 0 and 255, get rid of all the colour. That makes it a lot easier to work with. We also want to reduce down the resolution as well, because we don't need to have like a 4K image. We probably want to make it quite a crude image, because our model will be a lot smaller and therefore it'll be a lot faster for us to work with. So once we've got our grayscale image, we can then essentially split that. The way that the computer treats this is not as a grid as we see it with our eyes, like rows and columns, but just as a single array of values, of grayscale values. And those grayscale values are essentially just numbers. They're just a value between 0 and 255, which is just 1 byte of information per pixel. We then put that through a neural network. We'll have a look at how each neuron actually works in here. But a neuron is the model of a human brain cell. It has inputs, it has weights like levers and switches that we can move to adjust how it works, and it has outputs. And we can connect neurons to each other to create a whole network, a neural network of these neurons. And we have two sets of data, like I said. You can see on the diagram there, we've got the training data and we've got the test data. And we'll use the training data to adjust the weights in the model, and then we will test it at the output to see has it worked on data it's never seen before. And if it doesn't work, we get it to run again. And we do that several different times. Each one of those training sessions is called like an epoch. The number of layers in the model can define the sophistication and complexity of the model. The more neurons you have, the slower the model can run, and the more memory that you might need to process the model, but the more accurate it can be. And the output layer essentially has the result we're looking for. So it might say that there's a person detected in this object, this picture, or a SMARS robot, and it'll give it a confidence level on that as well. So how do these neurons work then? So we have a number of inputs. We might have several inputs. We might have a connection from the previous layer. Every single neuron might connect to this neuron. We have some weights in there, and the weights are essentially a way of dialing up or down how much value this particular neuron has. And the really interesting thing about how neural networks work is that we don't have to know what the neural network is doing behind the scenes. We just know that we put the values in, we run the training sessions, and we get the results we want. It's quite magical, and it's this weights changing that is really what the training does. It just says whether this should be a higher or lesser value. And what it will then do is it'll simply, if you look through the process here, we take the weight, we multiply each of the inputs by the weight to get a value, and then we add all those results together to get a number. That number is then normalized. We use a sigmoid function, which is like a maths function, to make it a value between 0 and 1. And that will then move on to the next. That can be an input to another neuron in the network. So MobileNet SSD. So SSD stands for single shot detection. This means we can run a process once through the image, and it will detect all the objects within that image. So they sometimes call this YOLO. You might see some of the model names at YOLO, you only look once, and single shot detection uses this YOLO. It's not you only live once, it's you only look once. It means we can detect multiple objects in a single pass through the image, and it means that the detection is fast as well. So MobileNet is one of the fastest models. Another technique we can use is called a Haar cascade. So this is it's quite an interesting thing to understand how it works, because not all the models have to use a neural network to do detection of features in a particular image. So what is Haar? So it's a mathematical sequence of rescaled image squares, rescaled square-shaped functions that form a wavelet. So you can see a little wavelet on the right-hand side there. And it's named after Alfred Haar, who was a mathematician. So let's have a look at how this works. So you might see these if you ever download OpenCV. You'll see all these different XML files, and these are the features that we can detect in a particular image set. So if we do the frontal face default, that can detect faces looking pretty much front on. So we take that one for example. So this works using feature detection. So a feature, they cascade. There's a number of different things it can look for. So we can do edge features. So we have a black and a white value, and these can be different sizes. They can be scaled to the size of their full image or right down to just like 2 or 3 pixels wide. We can do line features such as dark, light and dark. We can do that in all the different orientations, or white, dark, white, that kind of thing. Or we can do the 4 rectangle features to get sort of diagonal lines as well. So there's a little picture of me there. So if we're trying to find eyes, the eyes are darker than the rest of the face. So if you look at this from a grayscale perspective, my eyes will be darker than the rest of my face. You might see my mouth as well. But the fact that we have 2 eyes and we have a bit of a gap between and we have a nose feature, that can help us detect eyes. So if we apply the line feature as well as the horizontal line feature, that means that we can start drilling into what makes eyes appear on a face. So the nose is lighter on one side, for example, than on the other as the highlight hits it there. So if we find the eyes and the nose feature together, then we've got this cascade. So let's have a look at how this is going to work. So feature detection works by adding the values between particular pixels under the black area and comparing with the sum of the pixels under the white area. Because these are relative values, they're not necessarily, we don't want 100% black and 100% white, because that's not how images work. It's grayscales, and it might be more grey or more light depending on the lighting conditions in the image. So we need something that can work with that. So without any optimization, we'd have to scan every single pixel by pixel for each feature at every scale possible. So that's really not going to work. For a 24 by 24 pixel grid, that would be 180,000 possible features to test for, and that's just for the first feature, say like the light dark light feature. So that's really not going to work from an optimization perspective. And it's features all the way down. The algorithm looks for the first feature in the image. If it finds it, it can then check to see if the next feature is also in that sequence. If it doesn't find the first feature, the cascade can stop there, and it makes it faster because it doesn't waste time trying to do all the feature detections. It can just look for the first one and then the second and the third. So the way that it does this is the bit of maths I think is really quite impressive. So we have an idea of an integral image, which is an array of the values of the sums of the values of the image. We'll have a look at what that means in a second. And we have the original image, which is just this array of grayscale pixels. So if we have a grid, for example, on the right hand side there, that's a picture. These are the values that represent each of the pixel values. I've just done it as values between like 0 and 16, I think it is. But typically these would be between 0 and 255, but just to make this a bit easier to sort of show on screen. So we take this integral image. This is going to be an image that we create that has a special feature about it. So the algorithm will populate this integral image by calculating the sums of the values in the original image following a specific pattern. This is what makes it really quick to do. So if we understand this, we'll understand how these things work in the background. So each cell in our integral image is not a pixel. It can be just an area of the screen. So this could be 100 pixels wide, it could be just 1 pixel wide. And because we can change how many pixels that this actually represents, that means we can make it more accurate by having more pixels, but that might take longer, or we can make it really, really fast by making those larger areas. So we're going to calculate what the areas are underneath this particular integral cell, and we're going to calculate what the sum is of all the different values in there. We can then draw a line from the bottom right corner straight up and another going left. I'll show what this looks like on here. So we're going to take that little rectangle shape there, and we're going to add all the values of that of all the cells that are in that sort of purple area there, and we're going to put them in the bottom right cell. So in our integral image, that value is 51. So we'll plop that in there, and we've created one value in our integral image. We then do another area, so we can then get another rectangular area. We can add all the values under this sort of pink area. We can then put the total sum of that in the same space in the bottom right pixel on the integral image. And we can keep doing this until we fill the entire integral image. So this is what our integral image looks like. And you'll see there, we have low values from the very top to high values to the very bottom. And that means we can do some quite simple maths with just 4 numbers. So if we want to see, is there a particular feature in this rectangular area on screen here, we can do this very, very quickly, because all we need to do is just sum up a couple of numbers. So let's walk through this. So it says, let's select an area of the middle of our original image, find the sum. We can then use our integral image to quickly find this. So for a 5 by 3 pixels image, for example, we would have to add up all those at 15 numbers. But if we look at our integral image, we've already done that, and we can see what the value is there. But if we had to do this for 100 times 100 or 1,000 times 1,000, that'd be a lot of numbers to add up. But by building that integral image, we do that once for each frame of our video, and we can then detect these features. So the way that this works, we find the cell that corresponds to the bottom right hand pixel of the area that we're looking for on the screen. So this is our red box on this particular example. And we just need to remove some other parts of this so that we're just looking at this, because that 215 there is the sum of all the values above it and all the values to the left of it. So we need to take the values from that 80, which is just over here. We need to create a little rectangle on screen here and take away 80, take away 20, or add 20, and then take away 72. And that'll actually give us the real value of the pixels in this rectangle that we're looking for. So we're going to take away that 80 there. We're going to take away, or sorry, add to the integral that 20 there, and that other one, which is the 72, we're going to take that away. And that'll give us the true value, which is of 83. So why do we need to calculate what these 83 is? Well, if we're trying to figure out what a white area, what a black area, and what a white area is, we can then just compare these rectangles with each other, just those three numbers. So it makes it very, very quick to do feature detection on our integral image. So dramatically reduces the complexity. We've got some switches and levers to make this more accurate or less accurate, because we're not looking at pixels, we're looking at cell values, and we can detect features very, very fast. So that's how they work. If you like what I do and want me to make more videos like this, please give this video a like, drop me a comment, and if you're not subscribed to the channel as well, please subscribe. It means an awful lot to me, and I really love it when people subscribe. Okay, I do go live as well every single Sunday between 7 o'clock and typically 8 o'clock British summertime. So this is our model, just looking at this from a mobile net SSD and how all the different layers and things work. We get our image in, we run it through our mobile net SSD. We've got some other feature detection layers in there, convolutional layers that you sometimes call them, and then we get an output, which is a bounding box. It's like an X and Y coordinate and what the label is of the thing that's found in that area. We can have overlapping features as well. We'll see that when we run the actual example in a minute. I did a couple of model creations, like I said, in that Jetson Nano video a while back. A couple of things I found. The labels.txt file needs to be all lowercase. I know that sounds really straightforward, but I wasted about an hour on that. And the data path needs to have a leading slash, so it finds it from the root of the file system. It takes quite a while to capture all those 100 images, 1,000 images, 100 for each label that you're trying to find. And typically the training epochs are around 30 to 45 minutes, and that was on a Jetson Nano. So I believe the Raspberry Pi 5 can outperform that. So let's have a bit of a demo, shall we? So I have over on my desk over here, if I go to this image here, I've got this this little model I laser cut. Does anybody know what that is? My crude attempt. And we have a Raspberry Pi 5 in there, and we have the new camera module blue tacked to the front of the eye stalk there. This is my Dalek robot. And what we can also do, I can connect to the Raspberry Pi 5 in a couple of different ways. I'm going to show you the first way. So if I go to here, so I have got a remote desktop connection shared to this. So if you look at me in this little window over here, you can see me moving around quite quickly, whereas the image that's coming from the camera there looks like it's really slow, and that's because we're connected over a remote desktop connection. So that's not a very accurate way. So if I connect over here, this is the actual speed of the AI detection. So you can see there it says person. If I grab like this this water bottle here, Coke bottle here, you can see it says bottle. So it thinks it's about 78% sure, 80% sure that I'm a person. If I move my chair there, it'll also pick up that that's a chair there, you can see. So you can see that these are sort of overlapping, and it's fine with that. And it does sort of jitter about a little bit, and that's for a number of different reasons. It's running about 30 frames per second as well at the moment on that particular detection. Okay, so what I'm going to do, I'm just going to cancel that out there. Let me just move. So the reason that I've got this running on two different screens, if I go over to this one here, Sometimes it's easier to work in the remote desktop connection. That's a very unflattering picture. And sometimes it's just easier to work directly on the screen like this. If I put my little screen up there, for example, you can see I'm sort of leaning slightly off to the side because it's facing the other direction, sort of side on. What we can also do is zoom in a little bit on that example so you can see what's going on. Let me find that. I've also found every now and again this Raspberry Pi does seem to crash, and it seems to have done that right now, so I'm not sure why that is. So I'm just going to go back to me for a second. We're going to look through the code first. I've got a bit of a walk through the code, and then we'll run some more examples on there, I think. So let me just bring up my notes on my other screen, and then let's load up Visual Studio Code and have a bit of a deep dive into some of the Python code, which is one of the classification examples. And we can have a look in there. So I'm just going to load up Visual Studio. Just get my notes arranged there. There we go. And let me jump into the right window. So I want to have IMX 500. There it is. Let me open this locally. Otherwise, it might take. So I can do a. I share my screen on here. So why is that not playing up nicely? Just wait while that connects for a second. Let's just close that out. So what I will do, I will just clone down the library. That's probably the quickest thing for me to actually do, is just clone the example from Raspberry Pi. So they've got a really nice tutorial on this. So let me just create a new area for this to live. So if I just go down to my terminal, so I'm using Visual Studio Code here. I think it's a bit laggy just because there's like a lot going on my machine right now, so I just need to catch up for a second. So there we go. So once it's caught up, so that's intriguing. So my screen is not showing as fast as it should do there. Let me see if it's caught up. Not quite yet. This is the thing with live demos. So what I was trying to do is, there we go, is show you this kind of live on the Raspberry Pi, but it looks like it's crashed. But if I'm pressing the keyboard, I can see the caps lock light is going on and off. So I'm not sure why that's the case. If I type in the keyboard, yeah, that's working now. So we can do the demo in a second, which is good. Right, so I'm going to go back to the Visual Studio Code here. I'm going to load up the example and show you from here. So I'm just thinking about the best way to do this, given we're on a live stream. If I go over here, if I type in code and then dot, C-O-D-E. So I've got Visual Studio Code actually installed on the Raspberry Pi 5. So there we go. This is the classification code. Okay. So I'm just going to scroll to the very top of that, and we can start looking through what this actually does. Okay. So this script, this classification script, is going to find in real time objects within a particular image stream, and we can see what the different images are that it finds. There's like 1,000 different ones. So we're going to bring in argparse, which is a Python function for parsing arguments in a function. It's just a helper function. We're going to bring in time. We're also going to bring in the list from the typing library. That can just mean that we can define things as a list type. We're also going to import CV2. So CV2 is a, go back on here for example, CV2, has the stream stopped? Let me have a look. I don't think so. Alice is just saying about the stream stopping. It's not. It looks like it's fine. I'm just going to give it a second for people to catch up. I think what was happening there, Alex, is that the computer was basically just trying to catch up. There we go. You can see me back on there. Sorry about that. I think when I was launching Visual Studio Code, I think basically it was just like trying to catch up with itself, and the CPU was like maxing out. Anyway. So that aside, let me get back. I'm all over the show here. Let me go back to that code there. So the next line then, this CV2. So this is OpenCV, which is a computer library, computer vision library for Python. You can use this independently of the module. NumPy is the Python number library. It helps us do all kinds of math functions and deal with large sets of data. It's really good for manipulating images, doing things like RGB to HCV calculations, that kind of thing. We're going to bring in the Pi camera modules. We've got completed request, mapped array, and Pi camera 2, which just represents a camera. We're going to bring in the IMX 500, which is the new camera module helper function. And we're also going to bring in the post-process softmax, which thanks Anton for subscribing there. We're going to bring in that, and that's going to help us do the inference part of the detection. This last detections part, this is a list. I think it's a list or a dictionary of things that it's found, and then labels is the labels that we're going to load in there. So what labels has it actually detected? We've then got this classification class. So let me just find my notes on this one. So the classification is a simple class to store an index, the IDX, and a score of a classification result. So it's got a couple of member functions. It's got one that's called get label, one that's called parse classification results, parse and draw classification results, which will draw it on screen, draw classification results, which draws the label and the score, get args, which passes command line arguments such as the model file name, the frame rate, the softmax function, and the label file path. Right, so let me just scroll up on that one. So I'm using 3 different mices here. So the first function there, the classification one, you can just see we've got that in it. So it's just going to set up the index to be whatever we pass in as the index, and it's going to set the score to be whatever we pass in as the score. So that's just going to set things up when we very first run it. Get label. So we're going to pass in the request, completed request, and the index value. So it's going to retrieve the label corresponding to the classification index. So this is really just going to look in a text file, and it's going to find, so you can see there, we bring in the labels global constant. We if labels is none, then we open up the text file. So open args.label. So that's just bringing the command line argument as a read-only text file as the variable called f. So then we say labels equals f.read and split line. So it's going to read in one line at a time. Each line on in the file is going to be a different label. It's going to say assert length in labels is 1000 to 1001. So the labels in the file should contain either 1000 or 1001 labels. If it doesn't, it's probably the wrong file. The output tensor, sorry, there's a little helper thing getting in the way there. The output tensor size, so the IMX500.get output shapes request get metadata, that's going to give us a size of the tensors that it's going to return. The output tensor size equals 1000. So this is, we want to get 1000 results back and see what the values of each of those scores are. So what do we detect in a particular image? We're then going to return back the labels with the index value, which is what this function is about, retrieving the label corresponding to the classification index. Next up then is the parse and draw classification results, and as the little doc string there says, so it's analysing and drawing the classification results in the output tensor. So it simply just calls the function below, a bit over-engineered that. So parse classification results, this is going to parse the output tensor into the classification results above the threshold. So that is a fancy way of saying if it finds a person in the image and the person result, the score is above whatever the threshold is that we set, say like 50, then it will say that that is in the image. Otherwise, it's just noise. Because it will detect everything that we pass it in an image to some degree, but a lot of them will be like near zero. So these functions on here then, so no outputs is IMX500.get outputs. So it's going to get the metadata from the camera. If it's none, we haven't detected anything, then we just say return the previous detections, the last detections. NP is the NumPy. This is our function for doing NumPy functions, NumPy maths. So if the arg softmax, so this is the argument that's been passed through, if that is softmax, then we output whatever the NumPy output is. The top index is the numpy.arg partition. So this is going to create the top 3 indexes with the highest scores. So it's basically just going to do a find the top 3 scores and pass them to this top indices, and then it's going to sort them by their score. So this arg sort is going to sort them so that the top ranking one is at the top, second, and then third, for example. Then last detections equals classification index NP output index for index in top indices. So it's going to, for each of the things it's found, it's then going to go and grab what the name of those are. Draw classification results. So this is going to draw the classification results for the requested into the ISP output. So this little mapped array function will map the stream to the request. It's going to draw the region of interest, the ROI box. So it's going to draw a little bounding box around the thing that it's found. So it found a person face. It'll draw, for example, a red box around that. And then we can also draw put text ROI onto the text above the rectangle. So that's how we get that little label that says person. And then we have the actual box itself. And then we'll draw the labels for each of the ROI boxes that exist. So it's going to go through there into the results, check for each one, and then it's going to output that with a score as well. It then calculates the text size and the position. So we're using the Hershey Simplex font. That's part of the CV2 library, the OpenCV library. We've got like the opacity and the size of the font there as well. We can just say what the X and Y position of the font are to draw on the image. And then we create an overlay image. So overlay is m.array copy. So whatever we've put into that m array, we're then going to copy that as an image. We can then draw the background rectangle over the overlay. So CV2 rectangle, we put in the positions there. We say that it's a filled box, filled rectangle. We can give it an alpha value, so 0.3. That'll mean that we don't draw it 100%. An alpha value is like a transparency value. And then the added weight is a way of adding the two images together, the overlay and the original image, with a given alpha value. We then put the text on top of the results, and that's that particular function done. The getArgs one is just a way of getting command line arguments, and we're putting default values here so you can see what this is. So if we don't provide a model, it will use the mobile net version 2. If we don't pass in a frames per second, it'll just default to 30 frames per second. If we don't pass in type of processing, post-processing, it'll choose the softmax. We can preserve the aspect ratio, so we want it to be the same as what the camera is taking out, otherwise it looks stretched. The next one is the labels, the path to the labels file itself. So we can actually look in that ImageNet labels.txt file and see what that is. So if we go to the assets, which is where it says it is, we go to that ImageNet labels, there's 1,000 lines on there, and you can see these are all the things that it can detect. So there's lots of bald eagles, bullfrogs, green lizards. So there's 1,000 different things that it can detect. Quite impressive that it's got such an array of things. I'm not sure why they chose the things they did. But look, we've got Persian cats, all different types of cats and animals. So that's the different types of thing that we can find in there. So let's go back to here. And then there's the main function. So the first thing we do is get the arguments from the command line. We then grab the camera itself. We pass in those arguments. We then create a Pi camera, so we can do some image processing on that. We create what they call a config, which is essentially what is the frames per second. We could flip the image around if we wanted to, things like that. We then pass the show network firmware progress bar. So when we run this in a second, you'll actually see that it says updating firmware. So whatever is in the firmware currently, we'll overwrite that with this particular model that we've chosen to load there. If it's already in the cache, it'll work right away. Then we start the Pi camera, so we'll see the preview window pop up. It'll check that the aspect ratio is correct, and then it will do that parse and draw classification. And it'll keep running that until we quit the command line. So if we now run this code, we'll see all these different things happen. So if you watch this little command line box down here, rather than the image thing that pops up, see where it says network firmware upload, 33%, 40%, 50%. Once it gets there, the model it's loading is 4 megs in size, and then we have me. So we have a classification, so you can see there all the different things at the top of the screen that it's detecting. So we put a bottle there, look, it says beer bottle, red wine, wine bottle, that's what it's guessing there. Let's try, what else have we got? Can, there's got lots of drinks in front of me. So water bottle, paper towel, it said punch bag as well on there. I suppose it is kind of cylindrical. We have like a mobile phone, Polaroid camera, iPhone, iPod. It's trying to guess what it is. Does it know that that's a phone? It's not got iPhone on there. I guess it's quite old. So yeah, lots of different things that it can detect on there. So that's the classification one. If I do Command C a couple of times there, I should be able to quit out of that. Let's just do that. So that's one of the pieces of code. We've also got the object detection, which is what we were playing with at the very beginning. So let's do Python 3 and then IMX object. Let's do the MP one, like so. So it's just loading up that firmware again, because this is a different model that we're choosing this time. I can see on the camera itself there's like a little light that's flashing. So this time we've got the bounding box, and we've got the person and the how confident it is that I'm a person. It's only 85% sure that I'm a person. If I move my chair around there, you can see it's detecting a chair as well. And if we get that bottle back as well, you can see that it's also detecting that that's a bottle as well, which is quite interesting. Can it detect it from all different angles? Not necessarily, but it can detect it. It's occasionally detecting the screen there as well. And sometimes if I move the camera up, it can detect that as a bowl up there as well. If I move the eye stalk up a bit, see if I can get it to detect. That's a bowl. There we go. So yeah, that's how we can get this to work in Python and what the actual things mean there. So let's just quit out of that. There we go, and then back to me. Cool. Love live streaming. Okay, let's get back to our notes. So if you want to get yourself one of these amazing merch hats, you can do. It says Robot Maker on there, a jaunty angle. The real conversation starter. I've told this story before. We was in Italy, in Sorrento, and we sat eating an evening meal at this really nice restaurant, and there was a couple next to us, and the woman kept looking over at my hat every now and again. And after we'd finished eating, the woman sort of said, she said, "Do you make robots?" I was like, "Yes, I do." She said, "So does my husband. He makes the Da Vinci robot, which is like a medical robot, like a really sophisticated one." I was like, "I make robots not quite as sophisticated as that, but I do make robots." So it's a bit of a conversation starter, identifying yourself as a robot maker. So you definitely want to get yourself one of those, kevsrobots.com/merch for that. If you've not joined our Discord server, you can do that as well. Go to kevsrobots.com/discord, and you'll find everything you need on there. It's a growing community of people, and we talk about the code, robots. You can share pictures and all kinds of things. That's really loud. Why is that so loud? Oh, let me just stop that there. Sorry, I should have done this before this stream started. I usually set that to do not disturb. There we go, until tomorrow. So yes, we have the behind the scenes as well. If you want to check out that, and I'm on Instagram on all the other different social media networks there. So if I just go back to there, you can see what they are. So I'm on Threads at Kevin McAleer at threads.net, Kevin McAleer 6 on TikTok, on Instagram at Kevin McAleer, on X at KevsMac, on Mastodon at KevsMac at mastodon.social, and also Blue Sky at KevsMac at .bluesky.social on there as well. If you want to join me as well, you can do that a number of different ways. We had somebody just join just before the show started, actually. So you can do that by going to the Buy Me a Coffee site, so kevsrobots.com/coffee for that. You can join the YouTube membership program as well. That's just after you subscribe, that'll be replaced by a join button, and that's just the price of a coffee per month to help support the channel. There's also super chats and super thanks. You can do that. So super chat is if you're watching on the live stream now, you can do a super chat just by clicking that little dollar button near the chat window. And there's also the super thanks, which is if you're watching this on replay after the show is finished, you can do that same kind of thing there, and you'll get your name in the credits if you do that too. So I've got a number of different supporters I want to give a shout out to. So we have Sebastian, who has bought me 2 coffees in the past month. We've got Andy Brooker, who's a new Buy Me a Coffee member, so he was interested in the little robot arm that I produced. There's a new version of that now available on the kevsrobots.com website. Just updated that before the show. We've got Shemi, Alvaro, Marie, Jeff, Steve, Dion Corti, Marlene, and Tom on the Buy Me a Coffee memberships. And then on the YouTube side, we have Bello, we've got Orksrad, we have Littleback, Ford, Paul, Johnny, Handsome Cheerlights, Stephen Cross, we have John Paul Jolly, we've got Alistair, we have Cassie, Tinkering Rocks, Johnny, we have Michael, and we of course have Tom as well. So thank you to everybody who's supported the show. So that's the main part of the show over on YouTube, and I'll be showing you over here some other videos that it recommends you watch based on the videos I've created so far. We must be on a couple of hundred videos deep at this point, since we do at least one a week. So it's at this point in the video I'll say thank you so much for watching, and I shall see you next time.